One of the common problems when you read a chapter or you attend a lecture or watch a video tutorial or a video lecture is that you are going to be able to follow along. And if you do not have the capacity to ask yourself critical questions about what could possibly go wrong with what is presented to you, well, what you learn actually is just how this new technique that is being presented to you works in the most trivial and basic case that were the ones for which the technique was developed to start off with, okay? So what we're going to do in this video, we are going to revisit bounded types, but we're going to try bounded type parameters, but we're going to try to be a little bit more critical about what we expect from what we're learning about bounded type parameters. Okay, so this is take 2 on bounded type parameters, and the subtitle could be, I guess, so you think you got it. And you're going to see how most of you probably missed at first reading or at first viewing of the previous lecture those questions that we are going to explore right now. So the main theme for this slideshow is going to be taking a critical look and asking whether everything we were just shown how to do with bounded types parameter could actually be done just with polymorphism. It's a very, healthy attitude to have every time you're trying to learn a new technology, a new technique, a new tool, is to wonder, what is the difference really with the existing stuff that I already know about. And this is exactly what we are going to do in this lecture. So, more specifically, we are going to look at a situation where we are considering using a parameter in a method that is of type myClass, okay? And I'm going to assume that myClass here is a superclass in the hierarchy, the inheritance hierarchy of our application. So we are going to consider using the name of a superclass as parameter to a method, thus allowing, for example, if the superclass was number, to pass effective parameter arguments that are of type integer and double, for instance. Or instead of that, using the bounded type parameter notation that we just studied, which would be, for example, u extends myClass. So which one do we want to use? When do we want to use each of them? When are they equivalent? When does it make a difference actually to apply what we just learned about bounded type parameters? Because we knew already how to do things with basic polymorphism, right? Put the name of a superclass as a parameter, formal parameter in a method, and then suddenly you can pass argument to that method of any of the subclasses, okay? So let's take a look at a code example. We are going to start at the bottom of the slide. So we have two methods, display1, display2. The first method is going to use bounded types. The second method is just going to rely on polymorphism. So let's start with the second one because this is the one you should be the most familiar with. So public void display2 takes as parameter p a number. And the only thing it does is system.out.println of p. Okay, so we just want you to give me to give this method a number, so it could be an integer, a double, like any of those classes, okay? That subclass number, and we display it on the screen. So now the question is, I know how to do this with polymorphism. Now, if I apply what I just learned about bounded type parameters, what's the difference? So I write also a method display1. It also returns void. It's also public. But instead of having a parameter of type number, it has a parameter of parameter type u. And the parameter type u is defined here as u extends number. So we are going to expect this generic method, okay, this one is generic. We are going to expect this generic method to be called with a parameter, and the type of that parameter is going to be the type parameter u, and it's restricted to be number of one or one of its subclasses. So you should see already the similarity, okay? For all intent and purposes, those two methods seem to be doing the same thing. We have restricted the type of parameter that we can be given to be number or a subclass of number, but we did it in two very different ways. And one could argue that even if it's just because polymorphism has been around a lot longer than generics, one could argue that display2 is much easier to write and understand than actually the method display1, okay, that relies on generics. So let's use those two methods and try to find, where actually it makes a difference to go from generics and bounded type, to just polymorphism. So we put those two methods into a class named justTesting. This class features a main method. Here it is. Inside this main method, we start by creating an object of class justTesting. Then we create an object of class integer, and we put its reference in a variable named datum1. So that integer represents the value 42. Datum2 is going to be a double that represents the value 99.9. So now we have three objects, right? JT, which is a reference to justTesting, datum1, which is a reference to an integer, datum2, which is a reference to a double. And we are going to use the display1 and display2 methods that are defined inside the class justTesting. So we're going to call them by just saying jt.display1, jt.display2, okay? And we are going to pass to each of them both datum1 and then datum2. And we are going to see, if we get a compilation error, if there is any sort of difference at compilation time or even runtime, okay? And actually, all of those examples work out, meaning that when I pass an integer to display1, it's okay, because the type of the parameter is integer, okay, so integer replaces u here, and u is expected to extend number, which integer extends number, so we're good. When I call with datum2 is a double for the same reason, this is going to be acceptable. And then when I call display2, well, that you should be really familiar with, okay, I pass a parameter of class integer. Integer is a subclass of number. So yes, polymorphism works. It still works. So this is going to be accepted. And same thing when I pass a parameter of class double. I expect a number. Double is a subclass of number. It works. So this example is interesting because it shows no difference whatsoever between using polymorphism and using bounded types, as we learned to do in the previous videos. So it's not that good. It's not the kind of example that's going to help you understand why a technique, or a technology is actually useful. So we need to dig a little further. So what we're going to consider next is, okay, maybe this first example was too trivial. Okay, there was only one single parameter. So polymorphism is going to work just as well as bounded type parameters. So we need something a little bit more complicated. Let's go with an example where we have a method that has several parameters, all right? And so when we use a bounded type parameter, when you use the type parameter, we're going to say, well, this type parameter has to be the same for the first method parameter and the second method parameter. Let's take a look at an example. So what we have here is our class justTesting. Okay, nothing changed there. We have display1. Display1 now is taking two parameters, p1, p2. So we just display them again, nothing fancy in the code itself. Those two parameters are of data type u. U is a type parameter that is specified here by saying that u must extend number. So we just extended the previous example by adding a second parameter to our method that is of the same type parameter than the first one. And then for display2, we still use polymorphism. We say I have a number p1, a number p2. Okay. So let's start with display2. In the case of display2, clearly you could tell me already that we are allowed, because of the way we wrote the method display2, to pass a first parameter p1 that is an integer and a second parameter p2 that is a double. Okay, when we write number p1 comma number p2, there's absolutely no obligation for the data types for p1 and p2 to be the same. As long as they are a subclass of number or number itself, they're fine. Okay. Now the confusion and the difficulty comes sometimes from the fact that when you have this notation here that say I have a u that extends number, and then I'm going to use u for p1 and u for p2, there is sometimes an understanding that we define u as extending number, and it has to be the same for p1 and p2. Okay? Well, in this case, if we look at the static void main method, I have still my jt datum1, datum2 reference that are not changed. When I call jt.display1, datum1 and datum2, or jt.display2 with datum1 and datum2, they still work. They still work the same way. Okay? In the case of display2, well, we know why it works, because there's no relation, there's no constraint between the data type of P1 and P2. In the case of display1, the display1 method that is a generic one in our example, well, u can be inferred as being just number. We say that u needs to extend number, So if P1 is an integer and P2 is actually a double, I can make this work simply by considering that, by inferring that u is number. In this case, I go back to the same situation that I had before here with my display2 version of the method. Okay, so be careful about that. There's this misunderstanding sometimes that, okay, because of the syntax of generic method, it somehow implies that in this case we are going to enforce that whatever data type is used for P1 has to be used for P2. That is not the case. Type inference will actually look for a data type that matches both P1 and P2 and that satisfies this constraint that you need to extend number. And this can be done really easily by coming up to the solution, okay, u is a data type number. So does basic example fail? So we are still looking for something that is complicated enough to justify the existence of bounded type parameters, okay, to justify generic method and bounded type parameter as opposed to polymorphism. So we are going to keep complicating things a little bit more progressively, okay? So here's another example. We have a very simple inheritance hierarchy that has only two classes, bar and foo. The class bar extends the class foo, and that's all we need to know, okay? We don't care really much about the code in those classes. We just need to know which class pretty much is a superclass, which class is a subclass. And then we're going to, again, have two methods, one using polymorphism, one using bounded types and being a generic method. So let's start with the easy one. Do something two is the one using polymorphism. So we say that it takes one parameter, returns nothing, but takes one parameter named foo, and the data type of that parameter is list of foo. Now, do something one is a version of the same method that uses the concept of generic method and more specifically bounded type parameter. So it accepts a list of t as parameter, foos, plural because it's a list, okay? And we define the type parameter t as t extends foo. Okay, so this is getting a little bit more complicated now because now we have parameterized type where the parameter of the type t is actually a bounded type, okay? So we don't have just simple types for parameters. Let's try to use this method. So we define a list reference variable meant to hold a reference to an object of class list of bar. So far we have been using the foo class, which is a superclass. Now we use a subclass, and we create an object on the fly, a new array list of bar. So array list is an implementation of the interface list, so that's fine. We have an array list of bar object, and its reference is going to be stored to a list of bar reference variable. That's fine as well. See the rules that we detailed before about how we could do some degree of polymorphism with parameterized data types. And then we call our two methods. Do something one of list, do something two of list. So obviously the trap here, the thing that is the most relevant in this example is that we have a list of bar argument here, and we try to pass it to a method that expects a list of foo, let's do something two, and another method that expects a list of t, where t can extend foo. All right. So for the first method, It's okay, it's going to work. It's going to work because the type parameter t can be inferred by Java as being bar, okay? You expect a list of t, you pass a list of bar, I'm going to deduce that t stands for bar, okay? And that's fine, okay? T is supposed to extend foo, bar extends foo, we're good, no problem there. Do something to, when called with a list parameter, is going to fail. And this is because a list of foo, which is a formal parameter, the type of the formal parameter that's expected, is not actually a supertype of a list of bar. Okay, I refer you back to a few sections earlier in the lecture. Okay, if you have a list of string and an array list of string, yes, the relationship exists between them. If you have a list of foo, even though foo is a superclass of bar, a list of bar is not going to be a subclass of list of foo. Okay, that's not going to work. That's the one thing that we really talked a lot about, putting big warning sign there to let you know, don't go and assume that polymorphism works the same way when you deal with generic types. So here's the good news. I finally found an example that is complex enough so that there is a difference between a version of any method that use polymorphism and a version of any method that use generic types and bounded type parameter. Little bit of a problem though. We still have a little bit of a problem with this example. The issue with this example is that it's asking a totally different question. We didn't actually, when we implemented do something 1 and do something 2, we didn't actually replace a superclass, which was in our version 2 of the method, okay, so using polymorphism, by a type parameter that is extending that superclass. We didn't exactly do that here, okay? That's why I'm saying we are answering a different question. What we substituted is the parameter is a list of bar, and we're trying to shove it into a list of foo, which obviously doesn't work. So what would be the solution here? Well, this example is what is going to motivate us to study wildcard parameters, type parameters, okay? So what are they going to look like? Something like this. A list of unknown, this is how you read that question mark, extends foo. So I'm not going to go into more detail about wildcards. We are going to have an entire section dedicated to them, okay? But the point of this slide is to say, yes, we found a weird example that seems to point at a difference, but it's really not the same question that we started our lecture with, okay? We are not per se replacing polymorphism by a bounded type parameter, because here it clearly cannot work. Okay, the polymorphism in do something 2 clearly cannot work, and we know that from one of the previous lecture. So let's leave this example at that. Okay, for now, we'll work more on this kind of stuff when we cover wildcards. So let's backtrack a little bit. Okay, so we went maybe a little too far too fast. We felt the need for something different that we have not yet covered, a different technique. So let's go back to the idea of I want to use my type parameter for multiple method parameters. But this time, we're not going to just use, for example, the type parameter t for the first parameter and the second. We are going to use list of t for the first parameter of our add to list method, and t as data type for the second parameter of our add to list method. So our add to list method returns void. It takes a list of t and an element of class t, and as you can guess, it's going to call the add method on my list and tell it to add to itself the element that is passed as second parameter. So this is a generic method. Its type parameter is t, okay, that is used here for the list and for the element. So I can use it very easily. So that's the main difference, by the way. The main difference is that now we have t in a list of t instead of t standing by itself. So I can use it very easily. List of integer list equal new array list diamond operator, no parameter. So I have an empty list of integer, and then I say add to list to my list. the value 7. So autoboxing, 7 is turned into an object of class integer so that we can actually pass it to this method. So t is obviously integer because the second parameter is of class integer after autoboxing, and my list is a list of integer. So the Java compiler can infer that t should be integer. Everything is working, okay? And this is exactly what we expected. Nothing surprising there. This is out of the textbook, usage of this particular generic method. Now, if we use unrelated types, okay, so we have, for example, here a list of integer again, and we have the same method add2list defined as in the previous slide, but when we call it, we pass our list of integer as first parameter, and then we pass a string. So in that case, again, this was perfectly expected, nothing surprising there. We get the Java compiler to show us a compilation error. Okay, there is a problem indeed here. I cannot infer, what the data type has to be. You pass me a list of integer and then you pass me a string. Okay, so the type t is string because of the second parameter, but then the first parameter should be a list of t, so a list of string. No, it's a list of integer. What is the super type, between the two? There's a problem there, okay? So that's where the Java compiler gives up and say, you're not using this consistently. So again, no surprise there. But here's an example that would be closer to the previous slides where we started finding some irregularity, okay? Now let's say that I have two parameters. Okay, still my list of t and my element t, but this time I'm passing a list of integer as first parameter, which means Java should infer that t, as in list of t here, is integer. T is integer. And then my second parameter is 0.7, which is going to be auto-boxed into a float or a double. Okay, so that means that when I define t element, t stands here for double. Okay, so there's going to be a little bit of a problem here again. Right. So incompatible bound is actually the crux of the error reported by the compiler. Okay, so you are not capable to actually accept this in Java. So type inference is unable to find number as common denominator here. And it makes sense. It makes sense in the sense that a list of number is not a superclass of list of integer. So we are going back to that fundamental limitation of parameterized types, is that they cannot be used as you have been using regular types when you do polymorphism. Okay, so we are still bumping into the same thing here. So now, when we are using the parameter type t multiple time in a generic method, we have tried coming up with examples where t was appearing in a form or one over as qualifier of the data type of the first parameter from the method, and then also as qualifier of the data type for the second parameter of the method. We call very easy situation where we have, first parameter t p1, second parameter t p2. So we use t exactly the same way, and then we explored a little bit more complicated scenario where the first parameter was a list of t, and the second parameter was t. Okay, but now you can use also type parameters in your method when you want to qualify the return type of the method. We haven't explored that yet, so let's take a look and see what kind of example we can come up with here. So this time we want an example where the parameter of the method, one of the parameter or both or whatever, and the return type must be the same. So it's kind of like back to when we try to match the type of two parameters of a method. So we're going to write a static method called null check. It takes a value of data type t, so t is our type parameter, and a def value, a default value that is also of parameter t. What it does, it looks at whether value is null. If value is not null, it returns value. Otherwise, it assumes that, okay, because value is null, the user wants actually the default value that was specified as second parameter. So the way you would use it, for example, you have an integer in. Okay, this is a reference to an integer object, and it's null. So then you have an integer I, and you want to assign it a null check of in. So you look at whether in is null. If in was not null, I would return its value and store it into I. But because it's null, I'm going to get instead the default value that is specified as second parameter, in this case, 7. So after this call, when I system.out println the value of I get 7. That is okay. That is what we actually expected. Similarly, if instead of using an integer, right, I use a double, that's not a problem at all. That's not a problem at all. So my double null is dn. Then I call a null check on dn, and if dn is null, I want the value 0.7 to be returned instead. And that's exactly what happens as expected. All right? So where's the fun in that? Okay, that there was nothing surprising. So let's try to dig a little further. What about I call null check on I? So I is an integer variable, right, that is pointing to an object of class integer containing the value 7. So it's not a null reference, okay? It's a reference to an object of class integer. And then I pass D, which is a reference on an object of class double. Well, I'm going to get 7 out of it. So because the first reference is not null, I'm getting the value in that integer object. But the funny thing is that, yes, I did pass an integer and a double. And here, what I had is null check generic method that had one type parameter t that was supposed to be the same for value and def value. Well, not exactly. Just as we saw before, okay, type inference is going to find the common denominator here. And the common denominator here is number. So yeah, there is a superclass, of integer and double. It's number, and we can return that. And we can store here in a number n, which is how we declared our variable here to receive the value of null check. We can store in a number n the value that is returned by null check that was inferred to have to be of data type number. Okay, so a little bit more, to say, indirect, convoluted maybe, but still the same type of situation repeating itself. Okay, so we go through a lot of examples here so that you can then, when you review this lecture several times, re-listen to it or whatnot, you're going to be able to develop an understanding that allows you to unify all of these examples, unify the rules that apply to all those examples. Last thing we're going to discuss in this lecture, the previous example was okay, but we didn't try to downcast anything. So I'm going to explain to you what I mean by downcasting, and we're going to craft an example here that forces us to downcast. So let's start with the ground that we need to understand this example. We have a class animal. It's an abstract class with two abstract methods, eat and talk. Class dog extends animal, implement override eat, override talk. And we don't care exactly, it's probably just a system.out println, but the code itself is relevant. Then the class cat extends also animal, so dog and cat are both subclasses of the class animal. And just like dog, it overrides eat and talk, provide an implementation for those two abstract methods. Okay? What are we going to do with this example? Well, we are going to have two versions, again, of a single method. So this is a static method. It's called replicate. So it takes an animal as parameter, data type t. So t is my type parameter. And I specified that t extends animal. And then it does something, and it returns a reference also of data type t. Okay, so this is how we connect the return value to the parameter, like we said we would. And we have a version of this method that actually uses, is a generic method and uses bounded type parameter. And another method where we just said, okay, let's go with polymorphism, okay? So animal is my parameter. I call the method replicate polymorphism, and it returns an animal reference. So it's really similar to what we did in the previous slide, okay? There is, however, a little bit of a difference here. In the way that we wrote it with the bounded type parameter, whatever type t is passed as parameter is going to be returned. So if you pass a dog, you get a dog. If you pass a cat, you get a cat. Okay? If you pass an animal, you would get an animal. Okay? But animal is an abstract class, so we are never going to have object of class animal. So it's going to be dogs and cats, and the compiler does its job verifying that we pass appropriate data types, okay? But really the important thing is that whatever you pass is what you get. This is not true here. In the polymorphism version of the method, things are a little different. You accept an animal parameter, which means you can pass a dog, you can pass a cat, no problem. But you define here your method, return data type, as animal. So whether I passed a dog or a cat object to this method, I'm going to get a reference as return value that is a reference on animal. And what am I going to do with that? Well, the problem is to be able to use that reference, okay, if I passed to my replicate poly method a reference to an object of class dog, I'm going to have to cast the return value into class dog, and I'm going to have to do it by hand, okay? So that once the method is done replicating the object and returning to me a reference to a new object, well, then it's still a dog object, and I can use it as such, okay? So casting, making an explicit cast from a class like animal, which is a superclass, to one of its subclass is actually very often a problem, okay? In this case, you can feel that we have been giving up actually all those automatism that generics have been providing for us, and we are down to remembering what we call the method with and doing a typecasting on the return value to be able to use it, just as we use the parameter that we passed actually to the method, okay? So it's kind of like going backward. We're doing things by hand. We need to keep track of what we send to the method and cast it appropriately. So it sounds like, yeah, it sounds like a good case, you know, where generics could help. And yes, they can. They can, and they will, if we use bounded type parameter. So finally, we have an example here that is illustrating a concrete situation where you do not want to go with actually the polymorphism version, and it represents an improvement in terms of type safety to use a generic method, and more specifically, bounded type parameter. So I took the conclusion for this part of the lecture directly from the Stack Overflow article that I've been referencing. So I'm going to just read it out because I think it summarizes the situation pretty well, okay? The question is, when do we use a generic method with type bound parameter? And when do we just rely on polymorphism? Answer is just use regular polymorphism if you just want to handle specific classes as their base type, okay? So an integer and a double, for example, you are just going to handle them as numbers, okay? Upcasting is a good thing. Upcasting means you go from an integer to, for example, number, okay? But if you get in a situation where you need to handle specific classes as their own types, then generically use generics. And it's even better summarized by if you find that you have to downcast something, then you should consider use generics. In the previous slide, we found that the return value of that method, we had to systematically downcast it to a more specific class so that we could use it, actually, use the resulting object. That was a big red warning sign that we were doing something that could be done more cleverly using generics.